Okay, so just a few comments on nuclear physics here. So first of all, notation. Um, X here will stand for the element symbol. A will be the atomic mass number, and Z stands for just the atomic number. Now this equals the number of protons in the nucleus. The atomic mass number, of course, equals the number of protons plus the number of neutrons. So here we have a notation. X is an unknown. It's got a mass number of 97 and an atomic number of 43. So we just look in the periodic table and then find the element with the 43 atomic number, and we see here that it's technetium. So this has got to be technetium. And because the 43 uniquely specifies that it's technetium, we will sometimes, instead of writing it like this, we will just call it technetium 97, because technetium automatically implies 43. Now, there is the phenomenon of isotopes, which mean that there are going to be a number of different types of technetium atoms. All will have 43 protons, but the number of neutrons can vary, therefore the atomic mass can vary. Next, let's look at this. This is Pb is lead, plumbum, and the atomic mass is given, but the atomic number isn't. Y is an unknown, but we know it's lead, so once again we can just come over here, move this window out of the way, and find lead and see that its atomic number 82. So back here we know that this one has got to be it's got to be lead 210 82 atomic number, or just lead 210, because lead automatically implies 82 atomic number. Okay, so that's the notation. For next concept, the idea of the radius. How big is the nucleus? We spoke with the Bohr model about how big the atom was, but how big is the nucleus at the center? Well, typically we'll have something on the order of femtometers. A Fermi or a femtometer is 10 to the minus 15. Remember that with atoms we had something on the order of 100 picometers, and a pico was 10 to the minus 12, so you see there's about a factor of 1,000 there. And we can actually work that out. So if we had a nuclear size, it's about 10 to the minus 15 meters. And then an atom might be 100 picometers. That's 100 times 10 to the minus 12 meters. And so we see that's a ratio of, so that's 10 to the minus 10. It's about 1 part in 10 to the 5. So the atom is about 100,000 times bigger than the nucleus is, which, if you work it out, is probably the same order of size as a ping pong ball. Ping pong ball is probably about an inch, so that's on the order of about 2.5 centimeters. And BC Place, well, the football field would be 100 meters long. Add another couple of 100 meters for the seating, etc., say about 250 meters. And let's see what that is. That'd be 2.5 times 10 to the minus 2 over 2.5 times 10 to the 2. That's about 10 to the 4. So I guess it's 1 order of magnitude less, but you can get some decent visualization just from putting a ping pong ball at the center of a large stadium and realizing that that is about the ratio of the nucleus to the atom. All right, what else can we say about the size of the nucleus? Well, a nucleon, a single proton or neutron, all of these nucleons will be packed in really tightly, And as a result, we're going to make the approximation that the volume of the nucleus is approximately equal to the number of nucleons times the volume of one. That's not strictly speaking true because, of course, there's some airspace packed in between them, or an empty space, rather, packed in between them, but a reasonable approximation to start with. And we know that for a sphere, the volume is 4/3 pi r cubed. So we can solve that for radius. Solving for the radius, you'll get, it'll be 3. So if we put, first of all, put those two things together, it'll be n v naught is 4/3 pi r cubed. Solving for r, it's going to be n, and then it's going to be 3v naught over 4 pi. That'll be r cubed, but then we'll take the cube root to actually solve for the radius. Now, what we get then is the cube root of n, where n is the number of nucleons, and as the number of nucleons n, that is of course the same as the atomic mass A. And then what you have here is just going to be the radius of a single nucleon, because v naught was the volume of a single nucleon. Now, how much is that? Well, it turns out to be 1.2 femtometers, where again, femto is 10 to the minus 15. So here we have an expression for the radius of a given nucleus. It's based on how many nucleons there are in there. Take the cube root of that and multiply by the radius of a single nucleon, which as we see here is 1.2 Fermis, or 1.2 femtometers. So, and there Fermi is 10 to the minus 15. So for the two nuclei listed earlier, the first one was technetium, let's see, was it 97? Yeah, Tech 97. So back down here, here we go. Technetium 97. So A is 97. So the radius of that nucleus will be the cube root of 97 times r naught, which is the cube root of 97 we just had a small technical issue here. Okay, so I got my pen working again. So that's the cube root of 97 times 1.2 times 10 to the minus 15 meters. So what's that? We'll use this cruddy calculator here. So 97 to the power of a third, and then multiplied by 1.2. So the answer works out to be 5.51 times 10 to the minus 15 meters, or 5.51 Fermis. Okay, so that is the radius of Tech 97. The other example was lead-210. So this is the number of protons and neutrons, so that's the atomic mass number A. So the radius of that nucleus is the cube root of the atomic mass number times the radius of an individual nucleon. So it's just the cube root of 210 times 1.2 femtometers, or 1.2 Fermis, and again that's 10 to the minus 15. And you can work that out. It's similar. And then that then is the topic of nuclear radius. Let's see, will it fit here? Probably it will. There we are. Okay, next topic. Some nuclei are unstable and will decay, and they break up in the decay into smaller particles. The unstable nuclei are called radioactive. And the reason for the radio just has to do with the fact that when they emit gamma particles, which are bits of electromagnetic radiation, it's often at very high frequencies, radio frequencies. Okay, so in this decay we've got uranium-238. Uranium has atomic number 92. It's decaying into thorium-234, and thorium has atomic number 90. There's a couple of conservation principles that apply to these reactions. First of all, mass has to be conserved. So you got 238 nucleons here. You got 234 nucleons there. There's got to be another 4 nucleons there. Okay, so that tells you that this particle has to have a mass number of 4. Now, charge also has to be conserved. There's 92 positive charges here, 90 here. There's got to be another 2 charges there. So that this missing particle here has to have mass number 4 and charge number 2. Now, that is a helium atom, but we are dealing with reactions between the nuclei, and a helium nucleus is also known as an alpha particle. So putting that alpha particle in there balances the nuclear decay reaction. So it's really simple. You balance the top, which are the mass numbers. You balance the bottom number, which is the charge numbers. Now, inevitably, you'll have some larger nuclei, but also some smaller particles. And here is a list, a taxonomy of common little particles that get emitted in these nuclear reactions. The first one here is a beta particle, and this is called a beta minus particle. Let's just change the font here. So this is called a beta minus, but a beta minus particle is also an electron. You'll see that it has very little mass, so basically mass number is 0. You know, it's 1/2000th of the mass of a proton or a neutron, and it's got a charge of -1. This next particle here is a beta plus, and I'm not going to bother changing the font again, and that's sometimes called a positron. So it has a charge of 0, and a mass of 0 and a charge of +1. This next particle here is just a neutron. They're often emitted in nuclear reactions. This is a proton, mass of 1, charge of 1. The neutron has a mass of 1 and a charge of 0. Here's the alpha particle, the helium nucleus. This is a gamma, a little bit of electromagnetic radiation. It's got no charge and it's got no mass. Then lastly, the neutrino also has no mass and no charge, but it does have spin, and it comes up in balancing certain nuclear reactions. So let's balance a few nuclear reactions. So we've got nitrogen 14. So nitrogen 14, we'll look at the periodic table. Here it is, and we see that nitrogen has atomic number of 7. It's over here. There's nitrogen right there, atomic number 7. So back here we can say that's nitrogen, atomic number 7, and it absorbs an alpha particle, and then it decays into oxygen 17. Now we can see that the mass numbers aren't balanced, so there's going to be another particle over here with a mass number of 1. Oxygen has atomic number 8. You can look at it on the periodic table over here, and so 9 on this side. There's got to be 1 here, so we can see that this missing particle has to be a neutron to balance both the mass numbers and the charge numbers. Oh darn, I didn't want it to send that. So nitrogen absorbs an alpha particle, decays into oxygen 17. What's left over? Well, it's got to be a 1,1 neutron. Okay, next, sodium. Ooh, sodium. So come back here. So clear. Sodium 24. Okay, sodium 24. Now what's sodium? Sodium is 11. You can see it here. There's sodium right there. 11. So sodium 11, what does it do? It beta minus decays. So it emits a beta which has basically no mass but a charge of -1, plus something else. So what's this something else? Well, you can see it's got to have a mass of 24. And then there's 11 on this side. There has to be 11 on this side. That's got to mean a charge number of 12. Now the charge number, atomic number of 12, is magnesium. So the sodium will decay into a magnesium particle, a magnesium nucleus. Okay. And then we've got sodium 22, which beta plus decays. So what will that look like? So we'll have sodium, which always has atomic number 11. This isotope of sodium has atomic mass 22. It beta plus decays. Now you can look up higher on the page, or just remember a beta has no charge. A beta has no mass. A beta plus has a positive charge. So to balance mass, this particle's got to have a mass number of 22. To balance charge, it's got to have a charge number of 10. Atomic number of 10 plus 1 equals 11. It's balanced. Atomic number 10, again, you can look on the periodic table. That's neon. And those are some very simple notes on nuclear radius and on nuclear decays and the balancing of nuclear reactions.